So now talk about few different solver as well. So this is one solver what we explore is ICO-FSI form, and if we are working with the linear class of material and very small deformation, then that solver is enough. But normally in the real life we always go with the large deformations, and when we are observing large deformation, this solver will not going to work. Okay, so for that we have to go to another class of the solvers. Okay, so one solver that is available, okay, inside this open form extended version is yeah, this one, ICO-FSI elastic nonlinear UL solver. Okay, so let me open this particular solver. Okay, so this is transient solver for fluid structure interaction for an incompressible fluid and large strained solid. Okay, so it allows you to look at the large deformations. Solid mesh is moved using the U interpolated using least square methods. Okay, it take into account the larger displacement or the larger movement, and if we look at here the it's solid. Okay, so we have a two approach, Eulerian and back. So let me open Eulerian. Okay, so exactly the same code you can observe. Whatever I showed you at the beginning is inside this paper. Okay, so this particular solver is developed based on this particular paper algorithm. Okay, so similar class of the code you will observe in this area. Okay, whatever they are discussing, more like in the similar trend. Okay, so that is what is coded inside of this particular solver. Okay, so and it is also take into account the larger displacement. Okay, so with the help of this solver, if you there is a couple of standard tutorial is available, but I don't want to discuss this solver, that's why I didn't explore or didn't give you the idea about the tutorials. Okay, but if you go here you will see this Horn and Turek class of the tutorial. Okay, so but I want to explore this Horn and Turek type of the tutorial with a much more sophisticated solver. Okay, so it is called FSI form. So that is what we going to discuss as compared to this ICO-FSI elastic nonlinear UL solver solid solver. Okay, so but if you want to explore, you can use this solver for larger deformation as well. Okay, but more robust solver is another solver that we're going to discuss very shortly. Okay, so this is another very nice solver is available. Okay, so one can explore that solver as well, but what we I kept here, look, this one. Okay, so the same part, but I didn't discuss here. Okay, but I want to discuss another very nice solver, that is FSI form solver. Okay, so for that let me go to this area. Okay, so it is not readily available, so first we have to download it and then compile it, and then we're going to use that solver. Okay, so that is the idea behind that. So first let me open the area. Okay, so this is the place from where one can download it, and we are working with form extended 4.0. so what you have to do, you create one particular folder. Okay, so let me quickly do that. Okay, so what I'm doing, I'm constructing one dummy folder. I already downloaded and compiled it. Okay, so I'm creating an additional folder. Okay, in which I want to, let's say, compile this particular solver. So I say, okay, let's go to this area. Okay, and let's say cd that area. Okay, and now here they gave, okay, use this. Okay, and you able to download in this particular area. Okay, so here we are downloading this file. Okay, with this, then we unzip that file. Okay, So we are set with that particular file. Okay, so we go to that area. Okay, fine. Now before you start compilation, you have to source the thing. Okay, and then say wmac. Okay, so it going to take couple of minutes. Okay, so that is how you can finish the compilation and everything. Okay, so I just interrupted. After you finish, you just come out of that particular folder like this way. Okay, fine. And then you use this particular option. Okay, and with the help of that you can clean certain things that is required. Okay, so don't forget to just cut and simply select it and paste it here, and it's going to finish the job for you. Okay, so this is how you can download and install this FSI extended version of FSI form. Okay, so now I already did this. Okay, so I am deleting this particular directory. Okay, because I already have. So I constructed code as a additional folder. Inside that I did that part. Okay, so let me clean this area. Okay, so let come back here. So code is the place. Inside that I kept this particular folder. Okay, and I downloaded it, and when you download, you have a two directory you will see. One is the run and another is src directory. Okay, so inside the src directory or the required code is available. So in src you will see this solver. Inside the solver you will see FSI form. Okay, so let explore this FSI form. So finite volume fluid structure interaction solver based on a partitioning approach on a strong coupling. Okay, so this is a very, very sophisticated solver, and based on this solver this group publish a number of papers. Okay, so it is a well proven solver, and you can quickly adapt this solver for your own calculations. Okay, so this is much robust and I say strong solver as compared to what I show you both the solver. Okay, so if you want to adapt for any of your project, try to adapt this solver, not other these two solver. Okay, so inside you will see so many different type of the coding and everything, but we're not going to explore the coding area. Okay, out of this. Okay, if you want to manipulate or if you want to change the solver, you can go this area. Create solid mesh is just going to create the solid mesh. Okay, very quickly few important aspect I will show you. Now from here, if you go toward the this fluid form, okay, you will see the fluid form.c file. Okay, but solver part is somewhere else. I will show you where exactly you will see src, and here you have a fluid solid interactions. Okay, and here you will have a fluid solver, and inside the fluid solver you have a couple of options like ICO fluid solver, piezo based solver, or consistent ICO fluid solver. So normally we're going to use this consistence ICO fluid solver. So in the consistence ICO fluid solver, if you see, it is it try to look at this one entry. So I will show you where exactly you can tune the fluid solver. But inside this you will see the consistence.c file, and inside that you will see the evolve file. Okay, so evolve is the main area where entire code is coded. It is nothing but based on the our fluid solver algorithm only. Okay, so like we are solving the momentum equation, then we are correcting the velocities, all these things you will see. Okay, but they have a different approach as well. Okay, for that you will see couple of the things from this side. Same way, if you want to explore about the solid solver, you go to the solid solver area, and you have a this updated incremental, updated total Lagrangian approach. Whatever you want to use, you can adapt from this area, or you can explore the coding. Okay, so this is about the solid part coding. Okay, so based on updated Lagrangian approach or the total updated Lagrangian approach. Okay, so you will see all the coding part and required property reading and all the things inside of this particular area. Okay, so here you will explore all the required code for this particular test case. Okay, then 1 minute, we required include fluid solid interface. Okay, so that is what we required, fluid and solid interface. So that is what we have here, how we are taking into account the loading from fluid side to the solid side and solid side to the fluid side mapping, how we are dealing that, all the things, traction forces. Okay, all this thing you will explore from this particular file. Okay, so this is what you can see. Then certain utilities we have, function objects. Okay, so point history, how to add up the solid side probe. For that we require the point history that is available here. Then third party, some additional solver we required. Okay, like calculation eigenvalues and all this thing, they kept in this area. Okay, so this is how you can see the entire solver in this area. And then from the tutorial area, we have a couple of tutorial and we're going to solve all these 3 tutorials. Okay, so that is the plan. Okay, so let's come back to our FSI where we're going to solve our tutorials. So here we're going to solve these 3 tutorials. Okay, so that is the idea. So let's go to the first tutorial. Same way, we have a fluid and solid, both the things available. Okay, but what we required, we have to construct the link between solid and fluid. So we have to add up certain methodology before we go towards solutions. So this is how you will see. So exactly what is here, from the inlet we are applying some pressure pulse. Okay, and depending on that, let's say this is the tube, or let's say is the artery type of the things, and depending on this, our artery going is flexible and the wall is deforming. So this is the fluid side and this is the wall side. This is cut plane view of the our 3-dimensional tube. Okay, so that is what we're going to explore when we run the simulations. Okay, depending on the fluid motion, entire wall of the tube is vibrating or oscillating. Okay, so let's look at the readme file. So before that, okay, so let's go to the fluid directory only. Okay, so cd fluid, okay, so we are here now. Let's first clean the case. Okay, so we clean the case, then first go to the solid area and generate the mesh for solid part. Okay, so that is what we did with this command. Then we try to construct certain we try to use certain bash files and develop few things. So let's first explore that area. Solid side, we have this bash file. So what it's going to do, depending on this inner wall, it try to add up the face sets. So whatever the faces attach with this particular inner wall, we try to create the new name. Now you are aware, when we are working dynamic mesh, we are constructing for interpolation for GGI. Similar things we are dealing, because we want to define the interface between two type of the wall. For that we require this inner wall. Okay, and whatever the face attached to the inner wall, we are setting that face as the inner wall zone. Okay, so that is what needed. And in the similar line, if you go towards the fluid side, okay, inside the fluid side also we have a set bash, and like wall, we are saying the wall zone. Okay, so wall is the interface wall for the fluid side, and this inner wall So if you look at the pipe has an inner wall and the outer wall. Okay, so that inner wall is the interface between the fluid and solid. Okay, so but from the fluid side it is the wall only. So first we explore and then we open the mesh and try to have a look understanding about both of these things. Okay, so for that we are using this command to facilitate creation of that face zones, and then we say no flip flap, okay, to copy that in appropriate location. So this near wall zone is copied inside as a face zone, and that will facilitate us for the interpolation. Okay, now let's generate the mesh for fluid side as well. Okay, and then we say same thing, we are constructing the zones near to the wall, and then we say set no flip flap, that zone wall zone now copy as a face zone. Okay, so now let's open the paraFOAM and have an idea about the mesh. Okay, so this is our 1/4 of the our geometry. Okay, and if you see, this is the internal mesh and this is the wall. Okay, so this wall give us the interface between fluid and solid side. So let me open the solid side mesh as well. Okay, so for that let's go to the solid area. Okay, and let's say rename this as a solid. Okay, so now let me open the solid side mesh as well and have an idea about this interface. Okay, so this is our solid side mesh, close it, but we require the inner wall. Okay, so this is the inner wall from the solid side and fluid side. Okay, so this is how we have a interface between fluid side and the solid side. Okay, so this is exactly the interface between fluid and solid side. Okay, so we have this is fluid side, this is solid side. Okay, so that is and this particular wall give us the coupling between fluid and solid. Okay, so what we're going to do from the fluid side, after the Navier-Stokes equation solve, for this particular patch we take a loading from the fluid side in terms of the pressure and the viscous forces. Okay, as a traction force, and depending on that loading, now that goes as a boundary condition for the structure side, and the entire structure, within that structure we try to solve the deformation equations, and after the deformation equation we will see the motion for this particular patch, and then we first move the solid patch, and then we also try to we are not going to move in this particular solver the solid patch remain there, but accordingly we try to move the fluid patch. Okay, so that is the idea behind that. Okay, so this particular patch allow us to take into account the interface between, or it will facilitate the exchange of data between fluid and solid side. Okay, so that is the idea behind that. Okay, so this is how in this case it is one-to-one mapping, but not necessary. You have a completely different mesh for solid side and the fluid side. Okay, so depending on your requirement you can generate the separate mesh, and then you can add up the mesh inside the OpenFOAM. Okay, so this is what we did here. Now again let's come out of it and try to construct the link with the help of this command. Okay, and then we try to explore properties for this. So we constructed the link, it's already exist. Okay, so we require the link in the system folder, constant folder and 0 folder. Okay, so that is what required. So let's start with the constant folder and the solid property. So here we required properties. So for the solid property area, it allows us to choose what type of the solver or methods we want to use for the displacement. Okay, so we have a total Lagrangian or updated total Lagrangian, or updated incremental total Lagrangian. So we have two options: updated incremental total Lagrangian or updated total Lagrangian. Okay, out of this we are right now using this updated total Lagrangian concept we are using, and for that we are saying the outer character is 200, and the convergence criteria we set for the solid solver is 1e minus 7 and relative 1 1e minus 3. Okay, so that is what we set here. Then rheology property, so we say type is a linear elastic type of the material. Okay, so structure is a linearly elastic. Then rho is the density of the material, E is the Young's modulus, and nu is the Poisson's ratio. Okay, so all the property we set here. It is 3D, so plane stress equal to no. If it's 2D, then yes. Okay, so that is what we able to set from this area. Okay, along with that, what we require inside the solid side is the system folder. We have required certain setting, but before that, let's explore the setting from the fluid side, all these properties. Okay, so let's explore transport properties, then FSI property. Okay, so this is very important. Here we say solid patch name inner wall, solid zone inner wall zone, whatever we set as here. Okay, and this is the patch and this is the zone. Okay, so that is what we have to specify. Solid patch name, it is the interface boundary between the fluid and solid. From the solid side is the inner wall. Attached zone is the inner wall zone. Same way fluid patch wall, fluid zone wall zone, that is again we constructed with the bash file. This is wall and attached zone is the wall zone. Okay, so that is what you needed. Then relaxation parameter, interface deformation limit, outer tolerance. Okay, so until unless our FSI deformation reach 1e minus 6, okay, from the fluid side, okay, it will not going to stop, and total iteration we set for 30. That is the coupling iterations. Okay, and for coupling scheme they have a different type of the scheme, IQ and ILS schemes. Okay, so different scheme is available, they are using these schemes. Okay, coupled yes and predictor also yes. Okay, then fluid property. Okay, so inside the fluid property we can say it is a consistence ICO fluid. That is what I exactly told you when we look at the solver. So you can type whatever the fluid solver you needed in this area. Same way if you go toward the solid property, whatever the solid solver you required, you can type it here. Okay, then ICO fluid coefficient consistence, this is coefficient whatever needed. So n outer character is 3, non-orthogonal character is 1. Okay, so now we are not setting all this value inside the system folder, we have to set it in this area. Okay, then dynamic mesh, same way dynamic mesh and solver. Then velocity Laplacian we are using. Okay, and quadratic inverse distance with respect to wall. Non-orthogonal character say yes, least square volume point equal to yes. Okay, so this facilitate the mesh motion. And then let's go towards the boundary condition area. So here we have to specify the velocity u. Okay, so wall equal to moving wall. Okay, and at the inlet we say 0 gradient, outlet 0 gradient, because we want to specify the pressure at the inlet. Okay, so we specified at the inlet some time series of the pressure. Okay, and this time series we specify in the constant folder, sorry, in the here itself. Okay, so depending on the time what is the pressure. Okay, so what we did at the beginning, we specify the pressure and then we say pressure equal to 0. So we constructed one pulse. Okay, and then pulse is going to propagate inside the domain. Then point motion u. Okay, so point motion u, we are specifying the boundary conditions for every patches. Okay, so this is what boundary condition we have to specify for fluid. Same way solid side we require all these boundary conditions. Okay, so we are specifying point u and point d. Okay, same boundary, but d is our main displacement. So on the inner wall we are saying, let's say, traction displacement. Same way for the outer wall also we are saying the traction displacement. Okay, and this all part we saying is a fixed, it not moving. Okay, so that's why we say fixed value, and this is the symmetric. Okay, so that is what we have here. Okay, same way for dd also. Okay, so this is all the files is belong to the structural deformation area. Okay, so we have to specify the boundary conditions for structural displacement incremental. Okay, so if we are using with the this incremental total Lagrangian, then we require dd as well. Right now if you don't have, no worry, it's going to work with d only. Okay, so point and point dd. So this all, if you change the solver, this point dd is traction displacement incremental, then we require these boundary conditions. Okay, so dd is belong to incremental and d belong to total only. So this is all conditions we have to set. Then go to the system folder and let's observe the solution part. So p cell u, because we are working with a velocity Laplacian type of the solver. Okay, and then schemes as usual, all the schemes we have. Okay, then control, here we are using the point history, and it will facilitate us to extract the data like a probe within the solid. So inside the solid we keep this one probe for our how the solid is deforming and what is the displacement within that solid. For that we are adapting this point. Okay, and on that point we try to record certain its displacement quantity. Okay, so that is the idea. And along with that, in the this area you will see the scheme and solver. This whatever is control dict file, it is dummy file. Okay, it's not going to affect, but this two file is important from this area. So d and dd we specify the solver, then relaxation parameter you can specify here. Okay, schemes, whatever the scheme you want to use you can specify. Okay, so all these quantities you have to specify in this area. Okay, so now we are set for calculations. So let's come back to this area. Okay, and go to the fluid. Okay, and start calculations. Okay, so with the help of this one simple command. Okay, so now let me give you the idea. First let it finish, then yeah. So look, depending on which setting it going to work, have an idea about that part. Okay, so FSI fluid property, FSI property. Okay, so total outer character we fix equal to 30. Okay, so this is all our iterations. Total iteration goes as a 30. Okay, so look, for one time step it try to simulate multiple outer iterations. Okay, and within one iterations it try to solve the fluid side, solid side, and all other. Okay, but idea is that at the each iteration it try to calculate the current FSI relative residuals norm. Okay, so until this residuals is reach 10 to the power minus 6, it goes on and calculating that part. Okay, so when it reach 10 to the power minus 6, like here. Okay, so it reached 10 to the power minus 6. Look, it goes beyond 10 to the power minus 6. Okay, alternative FSI and this tolerance. Okay, after 16th iteration is then come out and goes to the next time step, and again simulating till this norm FSI. Okay, it reach till 10 to the power minus 6. Okay, so that is what setting we have here, and per one iteration first we solve for first we apply the this boundary condition and get the accumulated displacement for all the points. Okay, how much displacement one can see. Okay, that is what we have to specify. Okay, in the fluid property area. So that is very important, this two things. Okay, if you're not going to get a proper displacement, then you have to tune this parameter. Okay, so this two parameter is very important as far as the convergence and few things is concerned. Okay, then this cell motion u. Okay, so whatever the cell motion u we are seeing, okay, that is motion of a fluid side. Okay, so that is how one can see. So for that you go to the fluid side setting. Okay, so that is solutions. Okay, cell motion u. Okay, and that is what we have here. Okay, so until unless and how many Okay, cell motion U will be continue till it reach this tolerance, okay, 10 to the power minus 1. So that is what we are seeing. When it reach up to that, it will stop. Okay, then evolve the fluid solver. So for fluid solver we use the consistence ICO fluid, that is what we said. Then current number, solve for velocity and the multiple characters, that is what you see from this area. Okay, so if you are seeing that this is not converging fluid side, okay, so that is normal scenario in FSI. We will see the divergence in this fluid solver. Then what you supposed to do, then you go to the fluid property, okay, and tune this parameter, and it will allow you to stabilize the solver. Okay, then we set attractions of solid, okay, and fluid and solid tractions. Then evolve for solid side, we are using updated total Lagrangian, and we solve for solid. Okay, and then we check the our FSI residuals. If it is within 10 to the power minus 6 reached, then no problem, otherwise we come back and start iterating. Okay, so that is the what you see. Okay, so let's look at the results. So this is the fluid side. Okay, if you want to construct entire of the geometry, go to the area in the alphabetic, find out this reflect. Okay, reflect in x directions, then again tool, recent one, filter in y directions. Okay, and you're able to generate entire domain. Okay, and this is how our fluid domain is look like. Okay, now at the inlet we are specifying pressure pulse, and depending on that, when it propagate, try to give the enlargement to the our tube. Okay, so look, tube is deforming based on the pressure loading. Okay, so that is what you can see from this area. So I already run this case. Okay, so I just I will show you how exactly it look like. Okay, so that is what we started. So depending on the incoming flow, now fluid is passing through this flexible pipe. Okay, and depending on that, it try to move. Okay, so that is what we can see from this area. Okay, so that is very nice test case in the 3 dimension. Okay, now let's observe couple of few more tutorials in this area.